Hello, my name is Alli McCabe, and I'm a senior from Benicia, California, and I'm interested in environmental science.
Hi, my name is Gardenia, and I'm a senior from Austin, Texas, and I'm interested in environmental engineering.
Hi, my name is Audrey, and I'm a senior from Parsippany, New Jersey. I'm interested in neuroscience. We're a part of the NASA Seas Air Quality Initiative team.
So what defines air quality? Air quality is simply a measure of how clean or polluted the air is. One type of air pollutant is aerosols, which are airborne particles, also known as particulate matter, or PM for short. They are minute solid and liquid particles suspended in the atmosphere, which can come from man-made or natural sources, and can have adverse effects on human health.
We specifically focused on PM 2.5 particles, which are 2.5 microns or less in width. Particles this small, once inhaled, can travel deep into the lungs and can even enter the bloodstream, leading to health problems such as heart attacks and increased respiratory symptoms.
With each of us residing in different states spread out across the United States, our project focuses on our home states of California, Texas, and New Jersey on the county level. As shown in the table, these states have significant demographic differences. California and Texas are much larger than New Jersey in terms of both population and area. New Jersey also has a much higher percentage of urban land use.
Our group was interested in the correlation between PM and public and environmental health. Within public health, we investigated factors such as birth weight and asthma rates. Within environmental health, we examined vegetation health and coverage. This was measured by NDVI, or Normalized Difference Vegetation Index. NDVI gives information on the density of vegetation and is calculated using a mathematical formula determining the ratio of visible and near-infrared sunlight being reflected. We hypothesized that there would be a negative correlation between PM 2.5 levels and NDVI, as well as positive correlations between PM 2.5 levels, asthma rates, and percent low birth weight for all three states.
We first examined literature relating each of our factors and PM 2.5 particles to familiarize ourselves with the topic before finding our own correlations. For asthma and low birth weight, there was a positive correlation to PM 2.5, and for NDVI, there was a negative correlation for each of our three states.
We collected all of the data and images for all three states from the years 2014 to 2018 from the CDC National Environmental Public Health Tracking Network. Next, we compared PM 2.5 to the different chosen factors by importing the data into Google Sheets and generating scatter plots.
For NDVI, the CDC NEPH tracking network did not give data organized by county, but rather by individual census tracts. We wrote a Python program that averages the census tract values for each county in order to keep the geographic scales consistent. By creating scatter plots that compared each of the factors to PM 2.5, they returned R and R squared values that indicated the strength of the correlation between air quality and the other factors being studied. Values closer to 1 suggest strong correlations, while values closer to 0 signify weak correlations.
Here's a slider that shows two animated GIFs. The left GIF shows the average annual PM 2.5 level in California from 2014 to 2018, against a right GIF which shows the crude rate of asthma hospitalizations on the county level. The hatch mark patterns indicate data that is modeled. As you can see by the rise in blue counties over the 5-year period in California, air quality levels seem to worsen. When looking at the asthma hospitalizations, the general trend is that over time, across the counties, the rate is seen to decrease. On the right shows a scatter plot showing the correlation between asthma hospitalizations and PM 2.5 across the 5 years. As time progresses, the strength of the correlation decreases, as indicated by the decreasing R values. While correlations between asthma and PM 2.5 on the state level are weak, certain counties prove otherwise, such as Fresno and Imperial County.
The GIF on the left displays monitored and modeled annual PM 2.5 levels for Texas from 2014 to 2018. Many of the counties have hash marks, indicating that the data is modeled rather than monitored, which is due to the lack of PM 2.5 sensors throughout parts of Texas. The GIF on the right shows the prevalence of asthma in adults. Since the database we used did not have asthma hospitalization data for Texas, we chose to study the prevalence of asthma in adults instead. Due to data limitations, we were only able to generate a scatter plot showing the correlation between asthma prevalence in adults and PM 2.5 particles for 2018. Similar to that of California, the R and R squared values are low as well, but the counties of Cass, Brewster, and Kennedy seem to have higher correlation values between PM 2.5 and asthma.
The left GIF demonstrates the annual average PM 2.5 levels in each county of New Jersey from 2014 to 2018, while the other GIF displays the age-adjusted rate of asthma hospitalizations per 10,000 population. It is evident from the R and R squared values that New Jersey has a slightly higher correlation than California and Texas do. Both PM 2.5 levels and asthma hospitalizations decreased over the 5-year period, though the correlation remained about the same. The correlation was particularly pronounced for Burlington, Cape May, and Somerset counties.
Across the 5-year period in California, the general trend is that the percentage of low birth weight is seen to increase. The scatter plot shows that the R values between low birth weight and air quality are all close to zero, indicating weak correlations. However, certain counties, including Placer and San Bernardino County, indicate a strong positive correlation.
There seems to be no overall trend for correlation coefficients R over time, but the correlation for 2017 is significantly higher than for the other years. As seen in the scatter plot, there are weak positive correlations between low birth weight and PM 2.5 levels, though some exceptions are in Hemphill, Wheeler, and Kennedy counties.
The R and R squared values demonstrate that the positive correlation between percent low birth weight and PM 2.5 levels is higher for New Jersey than for the other two states. This actually supported our literature review, as one of the articles we read focused specifically on the link between these factors in New York and New Jersey. There also seemed to be a delayed effect of air quality on low birth weight in Warren, Sussex, and Camden counties.
NDVI, or Normalized Difference Vegetation Index, is generally seen to increase in California. As seen on the scatter plot, there is a negative weak correlation between air quality and NDVI.
The low R and R squared values for NDVI in Texas are seen to stay relatively constant. However, when comparing air quality and NDVI maps over time, there seems to be a sort of delayed effect between the two. In other words, changes in PM 2.5 levels for 1 year seem to be correlated with NDVI for the next year. The PM 2.5 and NDVI for Fort Bend, Culberson, and Duval counties appear to have higher direct correlations.
There was no significant change in vegetation coverage over the 5-year period, so it is difficult to accurately analyze correlation between PM 2.5 values and NDVI in New Jersey. However, the R and R squared values indicate a negative but very weak correlation, and a more significant correlation in the counties of Hudson, Morris, and Passaic.
Across the board, we found little to no correlation between air quality and asthma, low birth weight, and vegetation, despite the already established correlations from previous research. This seems to contradict the strong correlations found during the process of literature review, indicating possible flaws or weaknesses in the available data.
Some explanations for this could be a lack of PM 2.5 sensors available for data collection in the areas that are particularly susceptible to the public health and vegetation factors studied. The former is especially true for Texas, as many of the counties had modeled air quality data, rather than actual data collected from monitors.
Another potential reason for the contradiction between reviewed literature and collected data is the imbalance of access to medical infrastructure that could prevent accurate counts of asthma hospitalization and birth weight. The demographic differences may also point towards an environmental injustice regarding the availability of air quality sensors in at-risk communities. For instance, we pulled some data from the real-time air quality monitoring network Purple Air, which sells sensors at a price range between $199 and $299. This indicates that education level and socioeconomic status may also propose an obstacle to air quality and health.
To conclude, the scatter plots exhibited correlations that were different from the literature that was reviewed, which could have resulted from sensor data, medical, and demographic limitations.
In the future, we hope to analyze the correlations in specific counties within our 3 states, as well as extend the research to a larger range of factors.
We also hope to investigate the distribution of air quality sensors and to help determine which areas within each state are in most need of more sensors.
The SEAS program has reinforced my interest in pursuing future research where I can use Earth observation data to help end environmental and public health disparities.
The NASA SEAS program has allowed me to expand my horizons and explore STEM in a new way. I've been able to meet so many like-minded people, and this experience conducting real research has inspired me to pursue it in the future as a career.
The NASA SEAS program has been an incredibly valuable opportunity for me to conduct research alongside driven people, which has led me to discover my passion for it. We would like to thank NASA, Texas Space Grant Consortium, Globe Mission Earth, Center for Space Research, the University of Texas at Austin, Dr. Pippin, Dr. C, Femi, Yitong, and of course our mentors, Sara and Janene.
Thank you!